Hello everyone, welcome to my presentation about computational modeling of in vitro biodegradation of metallic scaffolds and bone implants. Talking about biodegradable metals, we're usually referring to magnesium, zinc, and iron. They have great mechanical properties while showing high level of biocompatibility and positive contribution to the metabolism of human body. Potential applications of biodegradable metals are cardiovascular stents and orthopedic implants. The main focus of the project is on the latter, acetable or implants for total hip replacements, in which we try to consider biodegradation behavior beside optimizing mechanical stability of personalized printed implants. But why should we consider biodegradability in this sort of implants? The issue is these implants should be removed and replaced at the end of their lifetime. But in the revision surgery, part of the newly formed bone is also removed along with the implant, making it difficult to achieve further mechanical stability. One of the greatest solutions to solve this problem is making at least part of the implant and the back of the implant from biodegradable metals, so it degrades as the new bone grows towards it. But there is still a challenge. We need to tune the biodegradation parameters to the rate of the regeneration of the new bone. In this project, this is solved. This is achieved by constructing a mathematical model of the biodegradation process. This model can be coupled with tissue engineering, tissue growth models, as well as considering the environmental effects such as the bioreactor environment or the human body environment. The model approach is underlying sciences are converted to mathematical models, and mathematical models are converted to computational models. The underlying science in this project are the chemistry of biodegradation, physics of perfusion for perfusion bioreactors, and biology of tissue growths. At this moment, the chemistry of biodegradation is only implemented. Mathematical models are a set of particle differential equations, mainly reaction, diffusion, convection, and also level set method, level set PD to track the moving interface of biodegradation. Computational models are mainly finite difference method, finite element method, scientific computing libraries, and open source solvers. So first, we need to consider the chemistry of biodegradation. The chemistry of biodegradation in this model is first the chemistry of the solution of metallic implant, the way that the metallic implant, in this case magnesium, dissolves through the medium, the formation of a protective film on the surface of the implant. For magnesium is magnesium hydroxide, and the effect of various ions in the medium on the elimination of this protective film, which increases the rate of biodegradation. In the second step, we have to construct the mathematical model. The mathematical model is constructed by converting the chemistry, a formation chemistry, to a set of partial differential equations. These partial differential equations track the change of concentration of various involved chemical species over time. But in addition to this, we need a method. We need to track the change of topology of the implant so we can optimize the mechanical stability of it over time. To do that, we need to track the moving interface, the corrosion interface. And for doing that, we used level set method. In level set method, we formulate the interface velocity, and by doing that, we derive a PDE that correlates the change of concentrations on the interface to the change of the morphology, in this case, a phi function. After constructing the mathematical model, we need to construct a computational model. This mathematical model is not feasible to be implemented in sophisticated software packages such as Abacus or ANSYS due to its complexity. As a result, we discretize the PDEs using sophisticated numerical techniques. Finite difference method is used to discretize time derivatives, and finite element method for spatial derivatives. And the mesh is also adaptively refined on the interface to increase the accuracy. The way that we construct a mesh is we have the medium domain, and we've labeled part of it as the scaffold, as the model, and then we refine the mesh on the interface of these two regions. The mesh generation in the model is achieved, is done by Saloom and Gmesh. The Vec formulation is implemented in FreeFEM, and according to the intensive computation we need to do, parallelization is achieved using high performance domain decomposition techniques and also high performance preconditioners and solvers. The model validation is taken place by experimental data obtained from immersion tests in two solutions, simulated body fluids and saline solutions. But the mass loss is measured indirectly via measuring the firm hydrogen as a side product of the corrosion. And the global pH is also monitored and is used to validate the model as the main criterion to validate the model. But before going for the final simulation setup, we need to estimate some of the parameters in the model, such as the reaction rates and diffusion coefficients. We had several parameters. We did a sensitivity analysis to get important parameters in different diffusion regimes, and then used a Bayesian optimization algorithm to estimate the effective parameters for SPF solutions and saline solutions separately. The main simulation setup is a narrow cuboid of magnesium in both solutions and simulating 21 hours of degradation. The computational models consist of 80 million elements and degrees of freedom of 3 million for each PD. We had 5 PDs, each with a degrees of freedom of 3 million. And the computational model is parallelized in 170 computing nodes on a supercomputer. The results show the formation of the protective film on the right and the release of magnesium ions to the medium. This the gray zone, the white surface, let's say, is the surface of the implant as it evolves over time, as it degrades over time, and indeed is obtained using the level set method. Here is an animation of the process, which shows how the implant, how these narrow surfaces, this narrow cuboid degrades over time. And here is the pH changes. In high diffusion regime, it means saline solution, and also the low diffusion for simulated body fluid. And for quantitative results, as I said, the validation is taking place by comparing the pH changes in experimental data and in the simulation data. And the results show a great compatibility, a great agreement between these two values, showing that the whole process of converting the chemistry to mathematical models and mathematical models to computational models is well constructed and well represents the reality. So in conclusion, we can say we have constructed quantitative mathematical model or semi-quantitative mathematical model to assess the degradation behavior of biodegradable metals. And by fully validating the model, after being fully validated, this model can act as an important tool to find the various properties of biodegradable metals, as well as improving the current workflow and the design process of these implants. Thank you so much for your attention.